Hey y'all. See who's here today. Alvin, I feel like you've been to my streams. I'm pretty sure you've been to a stream before. Okay. Not sure about Sabrina though. I have a really bad memory in terms of names. Like, you can tell me your name like 5, 6 times and I will remember. But hey y'all. Welcome back to another stream, I guess. I'm I usually wait like 2 minutes in to see if like any people come by. Let me see if I can fix my lighting. My lighting makes my face look really orange. I think that's gonna be it. But yeah. How's your week been? Anyone want to say anything? Guys. Oh, I kind of miss AP Physics. Such good days. Okay, let's see. See if all my materials are correct. Documents. Okay. Okay. Let's wait for 9:05. Say something if you can hear me. That would be very useful. Just drop a hi or hello in the chat. That'd be really sweet. I'd really appreciate it. Just want to make sure that I'm hearing people out there because it's kind of lonely up here. Hello? Okay, I'm not just assuming you guys are shy. I think the people on my last stream were pretty shy. Like only 1 or 2 people actually said anything, and there were like 5 or 6 people there. So that's okay. Looks like we have a new person here today. Abby? Abby, do you hear me? Say hi if you hear me. The stream hasn't started yet, so you haven't missed anything. But say hi if you can hear me. Or maybe my audio is just not working. My audio working? You guys not hear me? Okay, that's good. Looks like there's only 2 people here today, which is okay. Hopefully more people will like come swinging by. Have you been to a stream before? I feel like I should try to remember people who consistently come to streams. That's pretty good. Do you take AP Physics? Yeah, my streams are usually pretty small, but yeah, it must be weird to like see a stranger talk to you on screen. I understand that. I used to be paranoid like that. And I guess I'm one of those people now, so I can't really say much. But do you take AP Physics? Yeah. Oh yeah, just Physics 1 or both 1 and 2 or Physics C Mech? or physics C, E, and M, or maybe even all four. Uh, that's very good. I guess these streams could be very useful because we have our own curriculum for AP Physics. So as long as you keep on coming to streams, you'll basically have a free education, and it's pretty interactive. If you can't tell, I'm like talking to you, even though I'm a stranger on the internet. So I'm always here to answer your questions. Anyway, I'm gonna just like formally start this stream. So I always like to start off with an introduction. So I'm Casey. I'm a streamer for AP Physics at Fiveable. I go to school at Columbia University, and I am a second-year student studying mechanical engineering. So yes, I like physics. I took AP Physics 1 in high school, and I did get a 5 on that. So yeah, I've taken the test relatively recently, so I kind of remember what was on there, and I know what it's like to be a student. And on these streams that I usually do on Thursday, I like to just like do a general Q&A. So like any physics you have, you can throw it at me, and I'll try my best to solve it. And if you guys don't have questions, there are only 2 people here today, so I wouldn't be surprised if you guys didn't. Then I'll just go straight into practice problems, which is based on the lessons we have had during this week. So this week it was launch problems. So if you guys don't have any questions for me to begin with, I'm just going to do launch problems for an hour. Sabrina, do you have any questions for me? Like just general physics, you have a problem on homework you don't understand, or like, I don't know, anything for me to work with? Because I am down to do any form of physics. Anyway, accelerations in kinematics, that's very good because we have been covering accelerations in kinematics for a month. And I guess like projectile problems are mostly kinematics. I don't think there's much else to it. But I have a couple questions that mixes up a bunch of concepts together. Okay, anyway, I'm gonna just start doing practice problems. Let's see. Application window, 9.26 string. Okay. You see my screen? Okay. So, got a couple problems here today. I should probably keep an eye out to see any new people join. Hold on. Let me arrange my screen a little bit. There we go. Let me just widen this up. Okay. Kinematics. Classic. Let's do a teardropper, get the right colors. Oh, it's not getting the right colors. Why is it not getting? They keep on telling me to use the right colors, and they don't even use the right colors. Okay. Let's start off easy. I always like start off these questions super easy. I throw a ball straight up in the air and it comes back down 20 seconds later. What is the initial velocity of my throw? Okay. So when these balls go up and down, like the way I like to think about it is that if you just go one way, if you either go up or you either go down, it only takes half the time, right? Because it's symmetric. Go up at the same time and down at the same time. So this will take, going up here will take 10 seconds, and going down will take another 10 seconds. So if you use a really simple kinematics equation, so do you remember that x final is equal to x initial plus velocity initial times time plus 1/2 at squared? That's one of the kinematics equations you have on the equation sheet. And since we know that delta x is going to be some distance, you don't know that distance yet. And then delta x. And we know velocity initial is gonna, okay, because it's symmetric, I'm just gonna calculate for the downwards motion. I'm gonna just pretend that this is a drop question, right? Because the second half of this launch problem is just basically a fall starting at initial velocity 0. So I'm gonna just ignore this value and just have it equal to 1/2 at squared. Okay, so I want to solve for velocity, and I know that this value will be helpful later, just not right now when I'm trying to solve for t, which is time, right? So we're told that it takes 10 seconds to go back down. 1/2, we know the acceleration just universally is 9.81. And t squared is just seconds. 10 seconds squared is equal to delta x. If you don't know yet, if you want to solve delta x. Something else to note about general kinematics. You always want to make sure that your units cancel out. So if you have if you want delta x in meters, you want to make sure that this crosses out to come out meters. So let's say you have kilometers per hour and you don't realize that it's not right, then you're kind of in trouble. Like you end up having kilometers is equal to meters, or even worse, you might have kilograms is equal to meters and you know something's wrong. Like you want to make sure you cross out all of the units in your equation and see that once you cross it out, meters equals meters. Like you don't want something else. So, okay, let's solve this problem really quick. So this is basically 5 times 9.8, which is, darn, I have to actually use the calculator. Let's see. 40, it's about, delta x is about 49 meters, yeah? 1/2 acceleration times time squared. Yeah, so 49 meters. And we know that distance is equal to velocity times time. And we know that t is equal to 10 seconds. And it's 49 is equal to, 49 meters is the total distance. We want the velocity. Now, hold on. I realized I got ahead of myself. I need to use the original kinematics equation. Okay, let's take a step back. So we have delta x is equal to 49. So 49 meters is equal to velocity initial times time plus 1/2 at squared. Okay. Hold on a second. No, it was 49 for the t. I have a fish memory. Yes, it is 49. Okay, so 49 meters. Let's calculate for... Let me think about how to approach this first, actually. Remember how I said this was a drop questions? I can make this even simpler, right? So let's think about the situation at first. That this is just a drop question, and if you do acceleration times time, that is equal to velocity. Right? Yeah, actually, I didn't need to do any of that. Ooh. I went through all of that for no reason. I haven't been thinking. It's just 9.8 meters per second squared times 10. Just velocity. Which is just 98 meters per second at the initial throw, which is very fast, but it's unrealistic for the ball to stay up in the air for 10 seconds. But I also saw for delta x, which is 49 meters for no reason. Okay. Yeah, I was a little bit scatterbrained on that first one, but let's see if I can do the second one a little bit better. I launch a test rocket into the air and it reaches 100 meters, so we know delta x is equal to 100 meters. What is the initial velocity of the rocket? Okay, let's see. So we got 100 is equal to v. Yeah, so this is the same thing as a drop problem again, right? If you think about things symmetrically, everything is pretty much a drop problem if you have a vertical launch, and that's not the case for other types of launch projectiles. So we need to be more specific about this one. Okay, so you know that 1/2 at squared Okay, so 1/2 AT squared is kind of just a shortcut that I do when I know that, like, when I want to find delta x and I know that velocity initial is 0. So I know that 1/2 AT squared is going to give me the displacement automatically because of this first kinematics equation. So I know that 1/2 times 9.8 times t squared is equal to 100 meters, right? So 200 divided by 9.8, let's do that. 20.4. Oh, I should probably screw that. 20.42 to 0.5. 4.51. T is equal to 4.51. Initial velocity of the rocket, right? You got 100 meters is equal to velocity, which is in meters per second, and time, which is 4.51 seconds. Cross out time, and you just do 100 meters divided by 4.51. Is about 22 meters. Yeah, and if you look at this goes in one direction for 5 seconds and it reaches 100 meters, right? This one, yeah, that makes sense. That makes sense. Just checking my intuition here. Okay, horizontal launch. Looks like we have a third person here. Ari? Hi, Ari. So we're in the middle of doing like some practice problems. If you have any problems from like your homework or like just general physics, just drop it in the chat and I can get to it. If you have any concepts you want me to review, feel free to tell me. Let us continue to horizontal launch problems. I actually did a stream about this before yesterday on horizontal launch. And I kind of just broke down how to solve horizontal launch problems. So when you have horizontal launch, when we have vertical launch, we're only thinking about one dimension, right? Which is just the y direction. Right? And pretty much the only force you can have in the y direction is gravity. So you have gravity going down and you have the initial velocity. And that's pretty simple. But when you have a horizontal launch problem, that means that there's a vector going in the x direction. But pretty much the only force during a horizontal projectile's motion, the only force that exists is the downwards force, right? So basically you treat the horizontal portion as a regular kinematics portion, like just like how you would treat like a car going down a street. You don't really care about like the y displacement in that, unless there's like air resistance, but there's no air resistance in AP Physics 1. So I'm not too worried about that. So let's try this one. Let me delete this. Ooh. Okay, I launch another rocket. See, physics loves rockets. I launch another rocket, this time horizontally. It reaches the floor in 10 seconds and it travels 80 meters. How high did I shoot it from? So this is kind of let me ask you guys. Let's see if you guys want to interact a little bit. So how would you guys approach this problem? We're trying to find how high did I shoot. Right, so what do we need to solve first? Anyone want to say anything? Anyone? It's okay if you guys are a bit shy. I understand. But if you guys want to tell me what you guys think we should do with this problem, that'd be pretty cool. Because it's more fun with more people. Anyway. So we have this problem. And I'm going to find how high did I shoot it from. So we're given t, and we're given how far it traveled. So in the terms of x. So how high did I shoot it from is referring to the height of a problem. We're talking about the y displacement. Right, and remember how earlier I was telling you guys about how like the x displacement and the y displacement, like those two components are two completely separate components that you don't need to like consider when calculating other, unless it's in regards of time, this is exactly what I'm talking about, right? So we're given 10 seconds. So we're already given this connection between these two equations. We can like completely cut off the two now. So all we really need to do is solve a drop question, right? Just like the other problems that I did earlier. Just 1/2 acceleration 9.81 or 9.8 times t squared is equal to, 10 squared actually, is equal to height, right? And that's just 980, 490, right? Is that right? 50, yeah, sounds about right. Yeah, okay, 490 meters per second squared crosses out, and you have meters in the end. So this is right. So you see this information right over here, it traveled 80 meters. I completely disregarded it. It's completely irrelevant to the question because it's the x portion and we're only looking for the y portion. You guys understand what I mean? I accidentally dropped an apple I was eating while sightseeing. My hand was 10 meters in the air. How far away did the apple fall? Okay, so you want to find something in the x component, right? But we need t. You don't know what t is. So in these types of drop problems, you can solve for t by finding the y displacement. So we have 1/2 at squared. You notice how frequently I'm using 1/2 at squared. That's simply because 1/2 at squared is such a good shortcut for so many of these problems. So 1/2 at squared is equal to delta x, once again, plug in numbers, 1/2, 9.8. We're trying to solve for t, which is t squared. That's equal to 10. So 20 divided by 9.8, 104. Okay, let's solve for t is equal to 1.42. Remember seconds. Come on. Let me shift this all to the side. Okay. So, you know that our boat was traveling at 150 kilometers per hour. So the velocity, the horizontal velocity, before I drop it, is going to be 150 kilometers per hour. Oh, hold on. This isn't kilometers per hour. We don't want kilometers per hour. We want meters, because we're using meters today. Oh, we always use meters. So let's do some very basic dimensional analysis. 150 kilometers times 1 kilometer is 1,000 meters. And that 1 hour 60 minutes times 1 minute 60 seconds. Okay, let me plug and check these numbers really quick. Times 1,000 divided by 3600, 41.67. Kilometers, meters. Oh yeah, we want meters. Meters, hours, minute. Going at 41.667 meters per second. Okay. So we have velocity, we have time. That's just going to be an easy plug and chug. Distance is equal to velocity times time, where we do 41.667 times 1.42. 50 59.16 meters. Good to know. Always in meters. Okay. Let's see. Okay, you can tell that I'm making up these questions. I'm trying very hard to be creative because these drop problems are pretty much all the same, right? So I'm trying really hard to get really creative here. Okay. There is a marble on one of the seats of my car. I was going 70 kilometers per hour. I suddenly brake and then the marble falls from the chair. So pretty much I want you to neglect friction or neglect like rotational inertia, just neglect it. My seat is half a meter tall. How far did the marble fly? Okay, let's just do some basic diagrams. Once you get into courses, you'll love diagrams. But this marble just chilling here, right? Or I guess the marble's like right here. This is like my imagination when I came up with it. So the marble's just chilling right there. And then I suddenly brake and it just goes forward. Well, it drops to the floor, right? So you're going 70 kilometers per hour. So once again, you want to do the same conversion from kilometers per hour to meters, because I'm pretty sure the marble's not going to fly in a kilometer. So let's do that first. One kilometer times 1 hour over a minute times 1 minute. Also, you guys feel free to stop me anytime. Like, you guys don't understand anything, please tell me. Sometimes I get like really stuck in my head. Something that might seem like really obvious might not seem obvious to you, or what might seem obvious, like not really obvious to me, might seem obvious to you guys. So you never know. Help me out here. 19.44 meters per second. Okay. So our seat is a half meter tall. Okay. So we have 0.5. Okay. Yeah, once again, I'm using delta x is equal to 1/2 at squared. And this will be on your equation sheet, but I'm pretty sure we're going to have time afterwards, and I can tell you how to derive this equation. I feel like I derive this equation a lot because it just shows up in kinematics so frequently. It's really good to really understand this particular equation. Delta x, so 0.5 is equal to 1/2 9.8 times t squared. So, let's just approximate. Yeah. Actually, no, that's not. 0.5 divided by 5. 0.1 to 0.5. Hold on. My calculator is not letting me do this function. My calculator, as in my laptop, I just type in the spacebar. This is why I'm not efficient. 0.316. Okay. So t is equal to 0.316. Once again, distance is equal to velocity times time. And distance, we don't know, but velocity is going to be 19.44 meters per second times time, which is 0.316 seconds. Cross out, and we get distance in meters. Which in this situation, let's see how far a marble flies. 3, 1, 6, 8. 6 meters. So this will definitely hit the front of your car. Okay, let's put units, because units always good to have. Okay, you guys understand everything so far? Okay. I throw a ball at my friend and I throw it at 3 meters per second. Cliff is 20 meters tall. How far away should my friend be standing? Okay. So this is just another variation, so you want to find the delta x. Cliff is 20 meters tall. So once again, we can just do the classic drop problem. 1/2 times 9.8 times t squared is equal to 20 meters. Let's solve the t really quick. .019. Okay, that's just me solving this equation, which is just once again you have at squared equals 20. Cliff is 20 meters tall. How far away should my friend be standing? Okay, so we're just trying to find the distance, which is equal to velocity times time. And once again, it's just 3 meters per second times 2.019 seconds is equal to about 6 meters. Yeah, that sounds right. Okay. You guys have any questions so far? Just checking to make sure I have like understanding. I don't want to like get you guys lost here. Hold on. No one want to say anything? Let's just continue. Anything? Okay, angle launch questions. Okay, it's been a while since I've done these guys, but I'm pretty sure I'll be okay. Toss a ball at 60 degrees. Okay. So let's draw our problem out. Pretty steep. 60 degrees, right? 10 meters per second. Okay. So first off, I want to solve for the y component. So I should draw a better triangle. It's right angle. And sine, so we want this length, which is the height, which is the opposite of the angle, equals sine 60 degrees is equal to the opposite. The hypotenuse, and hypotenuse in this case is going to be 10 meters per second squared. Right? Let's do sine 60. What was sine 60? I should have memorized this from the unit circle, but I did not. I shall put it into the calculator. Sine of 60 can't be negative. It's not radians. I want degrees. Okay, sine clear. Sine of 60. 0.866. Okay. So sine of 60 is 0.866 equals opposite over 10. That means the height, the horizontal velocity, horizontal initial velocity is going to be 8.66 meters per second. And you know what? Because we're going to need it later, let's might as well solve for horizontal velocity. Cosine of 60 is equal to adjacent over hypotenuse 10. Let's put this into a calculator. Let's see. Cosine 60. Hold on. No, cosine 60 times. That's just 0.5, and 0.5 times 10 is going to be 5. Okay, so the y velocity, okay, Vy is going to be 8.66. Vx is going to be just straight 5 meters per second. Units are always important. Okay, so we have that. And we can pretty much solve for the rest, right? So to find the time it takes to drop, we can just do classic acceleration equals velocity times time. I'm gonna skip a few steps just like explaining how like the negatives work, but ultimately it just becomes like 9.81 is equal to 5 times t, 9.81 divided by 5. 1.962. So we have that one. I can just do classic distance equals velocity times time. It's really easy. Yes. $9.81. Wow. Life works in strange ways. Because this ended up being 9.81. So t is also going to be equal to 9.81. Wow. Algebra is incredible. Okay. I toss a ball at 45 degrees. Let me check back. Okay, so I launch a ball at 45 degrees with initial velocity of 15 meters per second. How high will my, typo, ball go? Okay. So I think sine of 45 and cosine of 45 are both equal. And they're both equal to square root of 2 over 2, and just square root of 2 over 2. Let me find like the normal person value for this, just to like check. Yeah, not at radians, I want degrees. That's 45. 0.7. Okay, let's just say just a straight 0.7. Let's just check if the cosine's the same, because I'm pretty sure it is. Yep. So we got 0.7, 0.7. Let's write that down. So we got 0.7 is equal to opposite over hypotenuse, and well, hypotenuse is going to be 15. Is equal to adjacent over 15. Okay. So just do 0.7 times 15, see what pops out. 10.5. So opposite. Okay, opposite is going to be Vy equals to Vx. Oh, I just had the number, I forgot it. 0.7 times 15. 10.5 meters per second. Okay, so once we have this, it's just a simple like just a simple drop problem, right? So acceleration times time is equal to 10.5. 9.8 t is equal to 10.5 meters per second squared. Don't get sloppy on those units. And then 10.5 divided by 9.8 is equal to 1.07. T is equal to. And then once again, after this, it's just simple. Distance is equal to velocity times time. So in this case, because we just divided out, I'm pretty sure it's going to be 9.8. No, is it? No, it's not. Okay, 10.5 meters times meters per second times 1.07 seconds. That's going to be equal to 1.07 times. It's equal to 11.235. Okay. Let's see. Oh, Taylor, have you been here before? I feel like you've been here before. Dynamics as in what? Okay. I'm trying to remember people who have been here. What are exactly our dynamics? Like, give me like an example of a dynamics problem, because I don't like. Oh yeah, those are fun. Okay, I'll go over them at the end. For now, we're going over launch problems. Okay, let's see. I'll guarantee you at least 10 minutes to that, okay? Because those are my favorite. I've been doing kinematics on these streams for so long. I'm like, wow, I miss everything else in physics. But keep on going. I toss another ball. There's so many balls in these types of kinematics equations. I toss another ball at 30 degrees. So let's draw our diagram. 30 degrees. It falls 20 meters away. Okay, this is actually a problem that I wrote up, and I wasn't completely sure how I was going to solve it, but it was like 2 a.m. or anyway, so I was like, I'll figure it out on stream. So if I can't figure this out, don't blame me. Falls 20 meters away. What was the initial velocity? Okay, so we have distance is equal to velocity times time, right? So we have distance, which is equal to 20 meters. It's equal to velocity times time, but we don't have t, we don't have velocity. We're trying to solve for velocity, right? So we're also going to have that like a times t is equal to velocity. Okay, we don't know the height yet, so we need to solve for the height. But we can know the ratio between a 30, 60, 90 right triangle, right? What was that ratio? Ah, gosh darn, I forgot basic geometry. 30, 60, 90 right triangle. Okay, I'm pretty sure there's not going to be a problem this difficult on like AP Physics, but I was writing this and I was like, why not? Okay, I remember this now. A to a root 3. So this is going to be a, what was the side? A root 3. A root 3 and 2a. Okay. So we got sine of 30. Okay, so we got a lot of unknowns, right? We got acceleration, we got time. Well, we need to find time, and if we find the velocity, the correct ratio of velocities, we should be fine. I think. I'm not completely sure yet. I wrote this problem without knowing what I was going to do. So sine of 30 is equal to opposite over hypotenuse, which is equal to, hold on, 1/2. Right, so the height, oh, I actually don't need to solve for this. I'm being dumb. That's why I made it a 30, 60, 90 triangle. Okay. So let's just say V, right? Let's replace this A with a V. So we know that X, velocity X is equal to V root 3. And let's just say that Vy is equal to just regular V, right? And let's just plug in those numbers and see what happens. So 20 meters is equal to V root 3 times t, and we know that 9.8 t is equal to V. So we got 2 variables and 2 unknowns. I think we can solve this. So 9.8 is equal to V over t, and let's just keep it at that. Ah, okay. I know how to solve this problem. Okay. So let's just plug in this 9.8 t back into this velocity, right? So you got 20 meters is equal to 9.8 t squared root 3. And then we can solve for t, and then with t we can solve for velocity, and with velocity we can solve for everything. So I don't know what the square root of 3 is. Let's see. 1.732 times 9.8. 16.9736. Divided by 16.9736. Ah, dang. Calculator's not working again. Okay. 1.17. Okay. So 1.17 is equal to t squared. Let's do 2 to the 0.5. 2 to the 0.5. So t is equal to 1.08. I'm pretty sure if you can solve this lunch problem, you can solve any lunch problem. Well, I don't want that pen. So, okay, let's leave that here. T is equal to 1.08. And distance, if distance is equal to velocity times time, right? So we know that velocity s is equal to velocity root 3. V root 3 times t, 1.08 seconds, is equal to 20. And we can just solve for it. Easy peasy, no problem. Plug in numbers. 18.51 divided by 3.5. Ooh, I did some wrong numbers. 10.686. Okay. Pretty sure you guys don't get any problems harder than that. And then I told Taylor that I would leave the last 10 minutes to working out some dynamics, but I did a lot of problem solving there. Let's see, let's extend it a little bit. Okay. Let's see. So this is a problem I got on my physics final in my first year of college physics. So this is a course that I take for my mechanical engineering degree. So I'm gonna go over it really quick. So I launched a 1 kilogram rocket into the air at 10 meters per second. So we got this boy right here. It's launched into the air 10 meters per second, right? Firecracker explodes and splits in half with 1,000 joules of energy released. The halves are equal in mass. How far away do they fall? So this incorporates a couple of things, right? So I'm not sure how far you guys are into like energy, but kinetic energy is known as 1/2 mv squared. Yeah, pretty simple. So let's incorporate a couple ideas. So first off, we need to solve for the height, for the final height that this is going to fall. So let's see. So let's see. Velocity is equal to acceleration times time, right? So we have the initial velocity. We know that the downwards acceleration is going to be 9.8. So we want to solve for how long it is in the air to find the distance as well, right? So 9.8 is equal to 10 meters per second. T. Okay, let's just round these numbers so that t is equal to about 10-ish. Yeah. So t is equal to 10. It cracks open, 1,000 joules of energy is released. So 1/2 mv squared plus 1/2 mv squared is equal to 1,000 joules of energy. It's quite a bit of energy. Halves are an equal mass, so they're 0.5 kilograms. All right. So the combined kinetic energy will be the total kinetic energy, right? I hope that makes sense a little bit, because like we technically haven't covered this yet. So this is going to be 0.5 v squared. I'm just combining these two together, equals 1,000 joules. And this is going to be a really big number. I did not think about this very thoroughly. Is it? It's just going to be 2,000. V squared is equal to 2,000. 2,000 to the 0.5. 44.72. So V is going to be 44.72 meters per second. So these guys are going super fast, right? And if it takes t amount of time to fall, they're going to, so one is going at the velocity of 44.72 meters per second. Since we know that distance is equal to velocity times time, we know that this is going to fall at 447 0.2 meters away. It's very, very far. And then we got the other piece, completely symmetric, right? Because they're two even halves and they have the same velocity. It's also 447.2. Add them together, and that's gonna be 447.2. I can't do simple multiplication. 89,444. Ooh, where's my? Okay, let's see. Taylor, I promised you to go over some good old classic dynamics problems. You know, I'm just gonna extend the canvas to the right or downwards. Okay. Oof. Scroll all the way down. So Taylor, I'm not sure what you're seeing quite yet, but I feel like the most advanced it gets is you have like this guy right here, right? And if you want to get super advanced, there is friction, but let's just assume no friction. You got two blocks. You got a pulley, frictionless pulley, because it's nice. Also massless, so there's no rotational inertia. And then you got another mass, right? Is this what you're trying to solve? Ah, sorry, Ari. Ari, are you talking? I only saw your message just now. Hold on, let me actually post. I'll actually post these solutions on Fiveable somewhere, so if you want to see them later. But also, let me drop the questions that I have made. I'll drop it at the end, so I'm not like taking up too much of your time. Okay, so for these types of questions, right? You want to think about forces. Force is equal to mass times acceleration, right? But in this case, the only force, so there's two forces acting on the thing, right? You want to find the total acceleration of the entire thing, right? So you want to find the total force that is acting downwards. Okay? So let's see. It's been a while. So of course you need to draw a force diagram. So you got normal force, you got gravity, and the force of tension, right? You got force of tension here. So because this is one line, I believe that that's like the same tension, right? Oh, that's a really patchy drawing. But you want to solve for, what is it? I want to solve for this. Okay, so we have this angle, right? We're usually given the angle of incline. Let's just do a nice 45-degree angle, right? 45 degrees is really nice. And the nice thing about 45 degrees is that like cosine of 45. No. What's like a nice cosine? Something a cosine is 0.5. I forgot what it was. Cosine 30? Let's see. Cosine 30. Let's get some nice even numbers. No, it's cosine 60, right? Cosine 60. Gosh darn it. I don't know which cosine I'm looking for. Cosine 15? Oh, I'm looking at radians. That's why it's screwing me. Okay. Cosine of 30. Cosine 60. Okay, cosine of something. Oh, come on. Sorry, I need to find something that's like really nice and simple to like make this super easy. Cosine of 60. Oh my god, I really forgot all of my cosines and sines. Okay. Regardless, you want to find like the force that is like acting on this tension in this direction. You can draw like a simple force diagram, right? So you got this angle. So you have like this angle. Hold on. Did I really forget everything about triangles? So this is just a lot of geometry. I really did forget everything. Hold on. So you have the regular normal force going up. you have the gravitational force going down, and you have tension force going in this direction. So you need to find the angle, given that this angle over here. Taylor, I seriously forgot how to do all of these types of problems. But basically, you want to know like what fraction of the normal force is being taken up by like the gravity. So typically, like if it's like cosine something, like I forgot what it was, is equal to like 0.5, that means like it halves the gravitational force, right? Actually, this is a trick that my TA taught me, right? Like if you want to find like the x displacement, not x displacement. Like if you want to like see like how like a change in x will look like, you usually use cosine because like this height will change and it'll take up like more height to like displace the gravitational force. Okay, you know what, Taylor? I actually need to review this stuff. I don't want to like teach you something that I don't fully understand. The clockwork load creates on a ship finds that there's a 20 try to continue to move in constant speed. Oh, okay, I can do that. I actually seriously forgot how to do all these questions. I need to review that really quick. Okay. Clock worker loading crates on a ship finds that 20 kilogram weight. Horizontal surface, I can do that. Okay. 20 kg. Okay, 75 newtons of horizontal force. Okay. Pretty simple. Constant speed. Oh, okay. So this basically means force is equal to mass times acceleration, right? So you have a 75 Newton force. Yeah, we have a 75 Newton force and you have a mass, and the acceleration is going to go in the opposite direction, right? So the direction of acceleration of friction always counteracts the direction of the velocity, right? Like the way you're trying to walk. So typically, like if you think about it, when you push something on like a harder surface, you can feel that there's a force counteracting you, and that is a friction force, and that's why it's always in the opposite direction, right? So we want to know like what is a force that will cause this to be equal, right? So if this force is equal to that force, the forces counteract and there is zero acceleration. Yeah. Newton's third. We're definitely not looking at the y direction. This is just like an x directional kinematic, not kinematic, like a dynamics problem. But yeah, if you coefficient of 60 at rest on a horizontal surface requires a 75 Newton force of 60 newtons. I don't know what that means, but if you want to find the frictional force, you just do 20 kilograms times acceleration. But yeah, the equal and opposite thing doesn't quite get into play until you have like the collisions, I think. Yeah, the collisions. So it's just like how, yeah, at least in these types of force equations, we don't really need to think about it. Yeah, basically, it's kind of an idea of like conservation of momentum a little bit, and Newton's third law. Okay. But anyway, your frictional force is just going to be 75 newtons over 20 kilograms. It's going to be newtons is in kilograms over meters per second squared, so we know that's the acceleration. Okay. I should really review how to do triangles, because I don't remember how to do triangles. But yeah. Okay. Anyway, that's the end of my stream. I'll make sure to brush up on, I think next week is forces, so I need to brush up on my force problems anyway. But yeah, hope this was useful. I think I'll be needing to upload this entire thing onto Fiveable. Yeah, I hope that's like somewhat helpful to you guys. Let me actually upload my stream questions. So if you guys, I know that if you want to look at my stream questions after this, you're gonna need to have like the Fiveable like special membership thing. So if you want to keep these questions, you better look at them now. So those are the questions. I'll leave it up for like 1 minute if you guys care. Pretty sure you guys don't care. But anyway, I'm gonna head out. I have homework to do. So much homework. Okay. I will be back next Thursday. So later.